In 1977, humanity launched a spacecraft into the darkness beyond the planets. 47 years later, Voyager 1 crossed what we celebrated as the edge of the solar system and entered interstellar space. Headlines declared victory. The mission was complete. We had reached the boundary. We were wrong. Voyager 1 has travelled for nearly half a century at 38,000 miles per hour and crossed less than 0.2% of the distance to the solar system's true edge. Not 2%, 0.2. The spacecraft that we declared had left the solar system will remain inside it for another 30,000 years. Every diagram of the solar system you have ever seen shows you roughly 0.1% of what actually exists. The rest, a sphere of trillions of frozen worlds stretching halfway to the nearest star, has been hiding in plain sight, written in ice and gravity, and the orbital mathematics of comets that have been trying to tell us the truth for centuries. Tonight, we rebuild everything you thought you knew about the size of home. If this revelation intrigues you as much as it should, let that curiosity guide you to like this exploration and subscribe for more journeys into the cosmos that surrounds us. The real solar system is about to be revealed, and you may never see the night sky the same way again. Prepare for a journey through scale, silence, and frozen infinity beyond comprehension. We begin. There is an image burned into your memory so deeply that you probably cannot remember the first time you saw it. A bright yellow sun sitting at the centre, Mercury close in, almost hugging the star. Then Venus. Then Earth, pale blue and familiar. Mars in its dusty red orbit. Then the asteroid belt, a ring of tumbling rocks. Then the giants, Jupiter with its swirling bands, Saturn with its magnificent rings, Uranus tilted on its side, and finally Neptune, cold and distant, sitting at the edge of the diagram like a quiet full stop at the end of a sentence. And then the image ends. The background fades to black. White text labels the planets. Maybe Pluto appears as a small dot beyond Neptune, a consolation prize for a world that lost its planet status. And that is it. The solar system is complete. Tidy. Ordered. Comprehensible. Something a child can memorize in an afternoon and carry for the rest of their life. You have seen this image on classroom walls, in encyclopedias, on the covers of science magazines, in every space documentary ever produced. It appears in textbooks from Tokyo to Toronto, from Nairobi to New York. It is one of the most reproduced scientific diagrams in human history, and it has been quietly, persistently, and almost completely misleading every person who has ever looked at it. Not because anything in the diagram is wrong. Every planet shown is real. Every orbit is accurate. The distances between them follow the laws of physics with extraordinary precision. The image is not lying to you in the way a forged document lies. It is lying to you the way a photograph of your living room lies, about the size of your house. The room is real. The furniture is real. But you have mistaken one small, warm, well-lit room for the entire building. And the building, it turns out, extends for light years, in every direction. The problem with the diagram is not what it includes. The problem is what it leaves out. And what it leaves out is not a minor detail. What it leaves out is almost everything. That familiar arrangement of 8 planets around a central star represents the innermost, brightest, warmest, most visible fraction of the sun's true domain. It captures the busy, well-lit core of a structure that reaches outward into darkness for distances so extreme that the entire planetary region, all 8 planets, all their moons, the asteroid belt, everything, becomes a pinpoint at its centre. Not a small portion, not a modest fraction. A pinpoint. A speck so tiny relative to the full structure that no diagram could ever honestly show both on the same page. Think of it this way. Imagine drawing a map of the Earth and including only your living room. The map is technically accurate. Your living room does exist, the walls are real, the furniture is correctly placed, but you have drawn one room and called it the world. That is precisely what every solar system diagram ever made has done. It has shown you the bright central room, and quietly omitted the fact that the house extends outward for an almost incomprehensible distance beyond the walls. The reason this matters is not merely academic. It matters because the way we picture something shapes the way we think about it. When you carry a mental image of the solar system as 8 planets ending at Neptune, you carry a model of home that is wrong by a factor so large it should genuinely disturb you. You carry the belief that beyond the last planet there is simply empty space stretching toward the nearest star, Proxima Centauri, some 4¼ light years away. A void. A gap. A desert. Between islands. That belief is not just slightly incorrect. It is spectacularly, almost laughably, incomplete. What the diagram never shows you is that the Sun's gravitational reach extends far, far beyond Neptune, far beyond Pluto, far beyond the most distant spacecraft humanity has ever launched. The Sun holds objects in orbit at distances so extreme that the light we send toward them today would take more than a year to arrive. It commands a sphere of frozen, silent ancient material that stretches outward until the Sun itself becomes just another star in a crowded sky. This structure has a name. It is called the Oort Cloud, and it is not a small addition to the solar system you already know. It is not an interesting footnote or a distant suburb. It is by volume essentially the entire solar system. Everything else, every planet, every moon, every asteroid, every comet currently blazing through the inner system, occupies a region so small relative to the Oort Cloud that the comparison defies ordinary language. The solar system diagram you memorized as a child shows you roughly 1/10 of 1% of the Sun's actual gravitational domain. Perhaps less. It is not a simplified version of the solar system. It is an amputation. A radical, necessary but deeply distorting cut that removes almost the entire structure and hands you a fragment, polished and labelled, while the vast dark body of the thing lies invisible beyond the edge of the page. And here is the cruelest part of the omission. It was not done through carelessness or deception. It was done because there is simply no way to draw the real solar system at accurate scale on any surface a human being has ever created. If you drew the Oort Cloud as a circle the size of a classroom wall, the planetary solar system at its centre would be smaller than the period at the end of this sentence. Not a small dot. The period itself. You cannot show both on the same diagram without making one of them invisible. So the diagrams chose the planets. They showed you the bright, visible, dramatic core, and they let the rest disappear into white space. The white space, it turns out, is where most of the solar system actually lives. This is the revelation that changes everything, not a new discovery, exactly. Scientists have known about the Oort Cloud for decades. The evidence for it has been accumulating since 1950. But somehow, despite all the space documentaries and science classrooms and online explainers, the true scale of what lies beyond Neptune has never fully penetrated the public imagination. The old diagram survives, the truncated model persists, and billions of people continue to carry in their minds a picture of home that is missing nearly all of home. What follows is the journey beyond that diagram, a slow, careful, honest journey outward from the sun, past the planets you know, past the boundaries you have heard of, past the edge of the solar wind, past the most distant objects ever visited by human machines, and into the frozen, silent, ancient sphere. That constitutes the overwhelming majority of the solar system's true extent. By the time we reach the outer edge of what the sun actually claims as its own, everything you thought you knew about the size of your cosmic neighbourhood will need to be rebuilt from scratch. The diagram lied to you, not with malice, but completely. It is time to see the real picture. Begin at the sun. It is easy to say those words and hard to truly feel them. The sun is not simply a bright object in the sky. It is a sphere of superheated plasma roughly 860,000 miles across, burning hydrogen into helium at its core, at temperatures exceeding 27 million degrees Fahrenheit. Every single second, it converts approximately 4 million tons of matter into pure energy. Not burns, not consumes, converts matter, becoming light, becoming heat, becoming the invisible pressure that holds the entire solar system in its gravitational grip. Everything within an enormous region of space orbits this star. Without exception, without negotiation. The sun's gravity reaches outward in every direction, holding planets, moons, asteroids, comets, and trillions of objects you have never heard of, in paths that curve perpetually around it. It is the anchor of everything we are about to explore. And to understand just how vast the sun's true domain is, we need to start small. We need to walk through the familiar territory first, step by careful step, before the real journey begins. Mercury sits closest to the sun, orbiting at roughly 4/10 of an astronomical unit. 1 astronomical unit, 1 AU, equals the average distance between Earth and the sun, approximately 93 million miles. Mercury huddles so close to its star that a year there lasts only 88 Earth days. The sunlight on Mercury's surface is 10 times more intense than what falls on Earth. It is a scorched, cratered world with almost no atmosphere, baked on one side and frozen on the other. Venus follows at 7/10 of an AU. Earth sits at exactly 1 AU by definition. This is the measurement everything else is compared against. Mars orbits at about 1.5 AU. These 4 rocky planets form what scientists call the inner solar system, a compact, relatively warm zone where solid surfaces exist, and sunlight is still powerful enough to drive weather, chemistry, and in Earth's case, life. Light from the sun crosses the entire inner solar system in under 25 minutes. In cosmic terms, these 4 worlds are practically sitting on top of their star. Beyond Mars lies the asteroid belt, stretching from roughly 2 to 3 AU. Despite its dramatic reputation, shaped by decades of science fiction films filled with dense fields of tumbling boulders, the asteroid belt is mostly empty space. If you flew a spacecraft through it, which several have, you would be unlikely to come close to anything at all. It is a sparse scattering of leftover rocky material from the solar system's formation, objects that Jupiter's enormous gravity prevented from ever gathering into a proper planet. And then, the solar system changes character entirely. Jupiter orbits at 5.2 AU. It is so massive that it contains more than twice the combined mass of every other planet in the solar system. Its gravity has shaped the entire architecture of the planetary region, scattering asteroids, deflecting incoming comets, and influencing the orbits of every other world around it. Saturn follows at 9.5 AU, its ring system spanning a distance wider than the gap between Earth and the Moon. Then Uranus at 19 AU, a pale blue green ice giant tilted so severely on its axis that it essentially rolls around the Sun on its side. And finally Neptune, the outermost planet. The cold, dark, distant giant orbiting at approximately 30 AU from the Sun. At Neptune's distance, sunlight is 900 times fainter than it is on Earth. The temperature hovers around -330 degrees Fahrenheit. Neptune takes 165 Earth years to complete a single orbit around the Sun. A person born when Neptune was at a certain point in its journey would live a full human life and die of old age before the planet returned to that same position. The Sun, seen from Neptune, is still bright enough to cast shadows, but it is a sharp, cold point of light, not the warm disk we know from Earth. Light from the Sun reaches Neptune in about 4 hours and 10 minutes. If you could drive to Neptune at highway speed without stopping, the journey would take roughly 5,300 years. You would have set off before the construction of Stonehenge and still be driving today. This is the boundary where almost everyone's mental map of the solar system ends. Neptune at 30 AU. The last planet. The edge of the diagram. Beyond this point, the popular imagination places only emptiness, a vast, featureless void stretching toward the nearest star, Proxima Centauri, about 4¼ light years away. That assumption feels natural. It feels obvious. It also happens to be one of the most consequential misunderstandings in popular science. But before we step beyond Neptune, it is worth pausing here for a moment and truly feeling the scale of what we have already covered. From Mercury to Neptune, the solar system spans 30 AU, roughly 2.8 billion miles at its widest point within the planets. Light crosses this entire distance in about 4 hours. Voyager 1, launched in 1977 and travelling at roughly 38,000 miles per hour, took about 12 years just to reach Neptune's distance. And Voyager was moving faster than almost anything humanity has ever built. These numbers are already large enough to resist easy comprehension. The distance from Earth to Neptune is so vast that no human being has ever truly felt it in their bones. We know the number. We can write it down. But the raw experience of that distance, the silence, the darkness, the cold, the isolation, is beyond anything our evolved minds can simulate from a chair on Earth. And yet, as staggering as those numbers are, they are about to become completely irrelevant. Because the distance from the Sun to Neptune, that enormous mind-bending span of 2.8 billion miles, represents less than 0.1% of the Sun's true gravitational reach. Everything we have just walked through, all 8 planets, all their moons, the asteroid belt, the entire familiar diagram, fits within a region that is, relative to the full solar system, essentially nothing. A bright, warm, busy dot at the centre of something so much larger that our language barely has the tools to describe it. The planetary solar system is not a summary of home, it is the front step, the porch light. The single lit window in a house that stretches for light years into the dark. Beyond Neptune, the solar system does not end, it transforms. It grows stranger, quieter, colder, and incomprehensibly larger. The familiar rules of planetary science begin to give way to forces that originate not just from the Sun, but from the galaxy itself. The journey outward has barely begun. What lies beyond the last planet is not emptiness, it is structure. Ancient, frozen, and vast beyond anything the classroom diagram ever dared to suggest. And the first hints of that structure, the first whispers from the dark, are already waiting just past Neptune's orbit, written in ice and gravity, and the slow elliptical paths of worlds that most people have never heard of. Step beyond Neptune, and something changes immediately. Not in temperature or light, those have already faded to their minimum. What changes is structure. Order. Predictability. Beyond the last planet, the solar system stops behaving like a neat clockwork mechanism and starts behaving like something ancient that has been disturbed. This is where the Kuiper Belt begins. Stretching from roughly 30 AU outward to about 50 AU, the Kuiper Belt is a broad disk of icy bodies orbiting the Sun in the same flat plane where the planets reside. It was not confirmed to exist until 1992, when astronomers David Jewett and Jane Liu discovered the first object beyond Pluto that was not Pluto itself. They had been searching for years, scanning the sky night after night, knowing that something had to be out there. The discovery was quiet, no dramatic press conference, just a faint point of light moving against the background stars, proving that the solar system did not simply stop at Neptune. Today we know the Kuiper Belt contains at least 100,000 objects larger than 60 miles across, and likely millions of smaller ones. These are frozen remnants from the solar system's formation, icy planetesimals that never gathered into a planet, preserved in the deep cold beyond the reach of the Sun's warmth. Pluto orbits here at about 39 AU. For decades it was considered the 9th planet. Then, as more Kuiper Belt objects were discovered, some nearly as large as Pluto itself, the definition shifted. Pluto became reclassified as a dwarf planet, one member of a much larger population. The change angered many people who had grown up memorizing 9 planets. But the reclassification was not a demotion, it was a recognition. Pluto was never alone out there. It was simply the first of many to be found. Light from the Sun reaches the outer edge of the Kuiper Belt in about 7 hours. This region is still relatively close to the Sun in the grand scheme of the solar system. It is a porch beyond the back door. It proves that structure exists past Neptune, that material orbits the Sun in organized patterns well beyond the familiar diagram, but it does not yet prepare you for how much farther the solar system actually extends. Beyond the Kuiper Belt lies something stranger still, the scattered disk. The scattered disk is a population of icy objects on highly elliptical orbits, flung outward by Neptune's gravity billions of years ago. These objects do not follow neat circular paths like the planets. They swing wildly. Some approach the Sun relatively closely, only to retreat to distances of several hundred AU, before slowly falling back inward again. Their orbits are chaotic, unpredictable, shaped by violent gravitational encounters that happened when the solar system was still young, and the giant planets were migrating through clouds of primordial debris. One scattered disk object, the dwarf planet Eris, orbits as far as 97 AU from the Sun at its most distant point. Another object, known simply as 2012 VP113, reaches even farther. But none of them compare to Sedna. Sedna is haunting. Discovered in 2003 by astronomers Mike Brown, Chad Trujillo and David Rabinowitz, Sedna follows one of the most extreme orbits of any known solar system object. Its closest approach to the Sun, its perihelion, is approximately 76 AU. That is already well beyond Neptune. But its farthest point, its aphelion, stretches to roughly 937 AU from the Sun. Sedna takes approximately 11,400 years to complete a single orbit. When Sedna last visited the inner regions of its orbit, human beings were just beginning to farm, building the first permanent settlements, inventing writing for the first time. And here is what makes Sedna so strange. Its orbit is too distant and too detached from the planets for Neptune's gravity to explain. Neptune is powerful, yes, but its influence fades with distance. At 76 AU, Neptune cannot reach Sedna anymore. Something else must have placed Sedna in that orbit. Something must have lifted it outward and parked it in a trajectory so lonely and so elongated that it occupies a region of space no known planet can account for. Scientists have proposed several explanations. Perhaps a passing star billions of years ago, when the Sun was still surrounded by sibling stars in its birth cluster, tugged on Sedna's orbit and raised its perihelion into the detached region where it now resides. Perhaps the gravitational tidal pull of the Milky Way itself, acting over hundreds of millions of years, gradually sculpted Sedna's path into its current shape. Or perhaps, and this remains deeply controversial, an as yet undiscovered massive planet lurks in the outer solar system, a world larger than Earth, orbiting in the darkness far beyond Neptune, its gravity responsible for the strange clustering of orbits among objects like Sedna. No such planet has been found. Searches continue. But the mathematics keep whispering that something massive might be out there unseen, pulling on the edges of the solar system in ways we have only begun to notice. Sedna exists in a transitional zone. It is too close to be part of the Oort Cloud proper, but too far to belong to the scattered disk. It occupies a kind of no man's land between the known solar system and the enormous frozen shell that lies farther out. Scientists sometimes call this region the inner Oort Cloud, or the detached population, a collection of objects that have been gravitationally decoupled from the planets, but not yet swept into the true outer cloud. Sedna is not alone there. Other objects have been discovered in similar orbits. Each one adds weight to the evidence that the solar system does not simply fade into emptiness beyond the Kuiper belt. Instead, it transitions, it stretches, it extends outward, through layers of increasingly distant, increasingly mysterious populations of icy bodies, each layer shaped by different forces, each one hinting that the Sun's reach is far, far greater than the last planet suggests. The existence of these objects, Pluto, Eris, Sedna, and the thousands of others orbiting in the cold darkness beyond Neptune, proves something essential. The solar system has structure beyond the diagram. Real, physical, measurable structure. Objects are out there, held in orbit by the Sun's gravity, following paths that carry them to distances the classroom poster never mentioned. But even these distant wanderers, as far as they travel, are still relatively close to the Sun. Sedna at 937 AU seems impossibly distant compared to Neptune at 30 AU. And it is. But 937 AU is still less than 1% of the distance to the Oort Cloud's outer boundary. The Kuiper belt, the scattered disk, even Sedna's vast elliptical orbit, all of it together represents only the outermost suburbs of the familiar solar system. The structures are real, the objects are there. But they are still well within the Sun's immediate neighbourhood. They still orbit in a region where the Sun's gravity dominates completely, where no other force seriously competes for control. What lies beyond them is different. Beyond Sedna's lonely aphelion, beyond the last detached object, the solar system enters a realm where the Sun's light has thinned to almost nothing, where temperatures hover just a few degrees above absolute zero, and where the gravitational influence of the galaxy itself begins to rival the pull of the Sun. Out there, in that vast and ancient dark, the Oort Cloud waits. Not a belt, not a disk, a sphere, a shell of trillions of icy bodies surrounding the entire solar system at distances so extreme that even light from the Sun needs more than a year to arrive. The first hints are behind us now. The Kuiper belt and scattered disk have shown us that the solar system extends beyond Neptune. Sedna has whispered that it extends much farther still, but whispers are not enough. To truly understand the scale of what surrounds us, we need proof. We need evidence. We need something arriving from that distant darkness, carrying the fingerprint of its origin, written into its trajectory. We need comets. There is a moment in the history of space exploration that should be celebrated for what it achieved and mourned for what it accidentally taught. On August 25th, 2012, a spacecraft the size of a small car, travelling at roughly 38,000 miles per hour through the outer reaches of the solar system, crossed an invisible boundary approximately 122 AU from the Sun. The spacecraft was Voyager 1, launched in 1977, and the boundary it crossed was called the heliopause. NASA confirmed the crossing nearly a year later in September 2013, after carefully analysing the data Voyager had sent back. The announcement was made at a press conference. Scientists spoke with measured excitement about what the spacecraft had detected: a sudden drop in solar wind particles, a sharp increase in cosmic rays from interstellar space, a shift in the magnetic field. Voyager 1 had entered a new realm. It had crossed from the region dominated by the Sun's outflowing plasma into the region where interstellar gas and particles take over. It was, by any measure, a historic achievement. Humanity's most distant emissary had reached a place no human-made object had ever been. The mission, designed to last 5 years, had survived for more than 3 decades and was still sending data from the edge of the Sun's influence. But then, the headlines arrived. Voyager 1 leaves the solar system, they declared. First human object to enter interstellar space. News anchors repeated the phrase with reverence. Magazine covers celebrated the milestone. Social media filled with illustrations of a tiny spacecraft crossing a glowing line labelled Edge of Solar System, leaving a neat bubble behind and venturing into the dark unknown beyond. The phrasing was technically accurate, in one narrow sense. Voyager 1 had indeed entered interstellar space, the region where the Sun's solar wind no longer dominates the local environment. But the headlines carried an implication that was devastatingly, spectacularly wrong. They implied that the solar system was behind Voyager now, that the boundary had been crossed. That home was over. Millions of people absorbed this narrative and filed it away as settled fact. The solar system ends somewhere around 120 AU. Voyager crossed the line. Story finished. But the story was not finished. It had barely begun. To understand why, you need to know what the heliopause actually is, and, more importantly, what it is not. The Sun does not simply shine, it exhales. From its surface streams a torrent of charged particles, electrons, protons, ionized atoms, moving outward in all directions at roughly 1 million miles per hour. This outflow is called the solar wind, and it is relentless. Every second the Sun loses about 1.5 million tons of material to this wind. It has been blowing continuously for billions of years and will continue until the Sun dies. The solar wind carries with it the Sun's magnetic field, stretching it outward like invisible threads woven through the fabric of space. This wind inflates a bubble around the Sun called the heliosphere, a region where the Sun's influence over charged particles dominates everything. Inside this bubble, the solar wind flows freely. Outside, the interstellar medium, the thin gas and dust between stars, pushes back. At roughly 120 AU from the Sun, the two forces meet. The solar wind, weakened by distance, can push no farther. The interstellar medium, composed of particles drifting through the galaxy, holds its ground. The boundary where they balance is the heliopause. When Voyager 1 crossed this boundary, its instruments detected the transition immediately. The density of solar wind particles dropped to nearly zero. The density of interstellar particles spiked. The spacecraft had left the Sun's plasma bubble, and entered the space between stars. This was real. This was measurable. This was a meaningful scientific milestone. But here is the critical fact that the headlines obliterated. The heliopause is not a gravitational boundary. It is a plasma boundary. It marks where the solar wind stops, not where the sun's gravity stops. And gravity reaches far, far beyond the heliopause. The sun's gravitational reach may extend to 100,000 AU or more, nearly 1,000 times farther than the heliopause. The sun is still holding objects in orbit at distances that would take Voyager tens of thousands of years to reach. Crossing the heliopause and declaring the solar system finished is like stepping off your front porch and declaring you have left your country. Voyager 2 followed its sibling through the heliopause in November 2018, crossing at approximately 119 AU. The data it returned confirmed what Voyager 1 had found, a sharp transition from solar-dominated space to interstellar-dominated space. The two spacecraft are now both flying through the interstellar medium, moving away from the sun at speeds that will carry them light years away over the coming millennia, but they are still inside the solar system. And they will remain inside the solar system for tens of thousands of years to come. The heliopause sits at roughly 120 AU. The inner edge of the Oort Cloud begins somewhere around 2,000 to 5,000 AU. The outer edge may extend to 100,000 AU or beyond. Voyager 1, after travelling for nearly 50 years, has crossed less than 0.2% of the distance to the Oort Cloud's outer boundary. At its current speed, Voyager 1 will reach the inner edge of the Oort Cloud in roughly 300 years. It will not exit the outer boundary for approximately 30,000 years. 30,000 years of continuous travel through the sun's gravitational domain before it finally truly leaves the solar system behind. The damage done by those 2013 headlines is difficult to overstate. They gave an entire generation of casual science followers a mental anchor for the size of the solar system that is off by a factor of roughly 1,000. When people later hear that the Oort Cloud extends to 100,000 AU, the number bounces off a wall of prior belief that says the solar system ends at 120 AU. The two facts cannot coexist in the same mental model without one breaking, and the one that usually survives is the one that arrived first, attached to a triumphant headline about a brave little spacecraft leaving home. This is not the fault of Voyager. The spacecraft did exactly what it was designed to do. It is not even entirely the fault of the journalists who wrote those headlines. The heliopause is a real boundary, and crossing it is genuinely significant. The problem is that we had no popular word for what Voyager actually did. Entering interstellar space while remaining inside the solar system, so the language defaulted to a simpler, cleaner and completely misleading narrative. The comfortable lie was not just taught in classrooms. It was reinforced by one of the most celebrated moments in the history of space exploration. And now, years later, that lie persists. Most people still believe Voyager has left the solar system. Most people still think the solar system ends somewhere near where the solar wind stops. And most people have no idea that the sun's true gravitational domain extends outward for distances that make Voyager's journey look like a short walk to the mailbox. The heliopause is not the edge of the solar system. It is a change in the weather. The property line is incomparably farther out, hidden in darkness, written not in plasma but in ice and gravity, and the slow elliptical orbits of trillions of frozen objects that have been circling the sun since the solar system was born. Voyager crossed the porch. The house stretches on for light years beyond. Something is arriving from the outer darkness, not once, not occasionally, continuously, and it has been arriving for as long as humans have been watching the sky. Comets, Not all comets, not the predictable ones that return every few decades like clockwork. Those are different short-period comets like Halley's Comet, which swings past Earth every 76 years, originating from the Kuiper Belt or scattered disk, nudged inward by the gravity of the giant planets until they settle into repeating paths through the inner solar system. No, the comets that reveal the Oort Cloud are the other kind, the long-period comets, the ones that arrive on orbits taking thousands, tens of thousands, sometimes hundreds of thousands of years to complete. They plunge toward the Sun from enormous distances, swing around it in a blaze of vaporizing ice, and then retreat back into the darkness on trajectories so elongated that they will not return for millennia. Some of them are making their first visit to the inner solar system since the solar system formed 4.5 billion years ago. And here is what makes them so revealing. They do not arrive from one direction. They come from everywhere. If you plotted the arrival paths of long-period comets on a map of the sky, you would find no pattern. Some arrive from above the plane of the planets, some from below, some from the direction of Orion, others from the opposite side of the sky. Their orbits are tilted at every conceivable angle relative to the flat disk where the planets orbit. There is no preferred direction, no clustering, just a random scattering across the entire celestial sphere. This randomness is not chaos, it is a signature. It tells scientists that somewhere out there, at distances vastly exceeding the planetary region, there exists a roughly spherical reservoir of icy objects from which these comets are being dislodged and sent tumbling sunward. The reservoir must be enormous to produce comets arriving from all directions. It must be distant to explain their orbital periods. And it must contain a staggering number of objects, because long-period comets keep arriving century after century, and each one that plunges too close to the Sun evaporates, lost forever, yet the supply never runs dry. New comets keep coming. The reservoir keeps sending them. This is not speculation. This is orbital mechanics. The comets are real. Their trajectories are measured with extraordinary precision. The mathematics demands a source. Consider Comet Hale-Bopp, which appeared in 1997 and became one of the most widely observed comets of the 20th century. It was visible to the naked eye for 18 months, a brilliant visitor that millions of people watched from their backyards. Astronomers calculated its orbital period at roughly 2,500 years. Its most distant point, its aphelion, sits at approximately 370 AU. Hale-Bopp spent millennia drifting in the cold outer reaches before gravitational forces redirected it inward, where it briefly became a spectacle, before retreating back into darkness. Or consider Comet Hyakutake, which passed Earth in 1996. Before its encounter with the inner solar system, its orbit carried it to an aphelion somewhere around 1,000 to 2,000 AU. After its passage, gravitational interactions with the giant planets dramatically reshaped its trajectory, stretching its new orbital period to roughly 70,000 years, with an aphelion now reaching approximately 3,400 AU. Hyakutake arrived from a region so remote that when it last visited the inner solar system, modern humans were still living in the Ice Age, painting animals on cave walls. Then there are comets whose orbital periods stretch into the hundreds of thousands or even millions of years. Objects arriving from aphelions tens of thousands of AU away, deep within the outer Oort Cloud. These are the most direct messengers. Each one carries frozen material that has remained virtually unchanged since the solar system formed. Their chemical compositions provide snapshots of the primordial disk from which the planets were born. And their trajectories, arriving from every direction in the sky, confirm the spherical geometry of their source population. More recently, Comet C 2023 R3 Pan-STARRS, discovered in September 2023 and confirmed by the Minor Planet Center, drew attention as another long-period visitor from the outer solar system. Astronomers classified it with a steep orbital inclination far above the plane of the planets, exactly the kind of trajectory expected from an Oort Cloud origin. It reached perihelion in April 2024 at a distance of roughly 47 million miles from the Sun. Its full orbital period remains uncertain because only a short arc of observations exists, but it could span thousands of years. Comets like this arrive regularly. Each one is a fresh data point, confirming that the distant reservoir is still active, still populated, still sending members inward on trajectories shaped by forces operating at the very edge of the Sun's gravitational reach. But the evidence does not stop with their arrival directions. It is written into the numbers themselves. When astronomers calculate the aphelia, the most distant orbital points, of long-period comets, a pattern emerges. Many cluster around a specific range of distances, roughly 20,000 to 50,000 AU from the Sun. The clustering is too tight to be coincidental. It points toward a specific structure at a specific distance. A vast cloud of icy bodies orbiting at the outermost edge of the Sun's gravitational domain. This clustering was first noticed in 1950 by a Dutch astronomer named Jan Oort, and it became the foundation for everything we now understand about the solar system's outermost structure. But we will return to Oort and his insight in a moment. For now, what matters is this: the comets themselves are the proof. No human has ever seen the Oort Cloud. No telescope has ever photographed it. But every long-period comet that blazes across our skies carries the fingerprint of its birthplace written into its trajectory. The orbit does not lie. The mathematics cannot be faked. The comet came from somewhere, and that somewhere must be real, must be distant, and must be shaped like a sphere surrounding the entire solar system. The comets are messengers, frozen couriers launched from the dark edge of the Sun's domain, carrying news of a structure so vast that the entire planetary solar system becomes a footnote at its centre. They arrive covered in ice that has not melted in 4.5 billion years. They glow briefly under the Sun's heat, shedding dust and gas into brilliant tails that stretch for millions of miles, and then they fall back into the darkness, returning to orbits that will carry them outward for thousands or tens of thousands of years before they swing back again. Some will never return. Perturbed by Jupiter or Saturn during their passage, their orbits are altered just enough to send them spiralling out of the solar system entirely, ejected into interstellar space, lost forever. Others will make the journey again and again, slowly evaporating with each pass, until nothing remains but a trail of dust. But for every comet lost, the reservoir sends another. The Oort Cloud is so vast, so densely populated with trillions of icy bodies, that the supply seems inexhaustible on human timescales. It has been feeding comets into the inner solar system for billions of years. It will continue for billions more. The messengers keep arriving. The evidence keeps accumulating. The mathematics keeps pointing outward, toward a structure hidden in darkness, at distances the human mind struggles to hold. And the message they carry is simple, undeniable, and profoundly unsettling. The solar system does not end where you think it does. In 1950, in the city of Leiden in the Netherlands, a Dutch astronomer named Jan Oort sat down with a collection of data that would change the way humanity understood the solar system forever. He was not looking at photographs. He was not peering through a telescope. He was simply studying numbers, orbital data from 19 long-period comets, each one carefully tracked and measured as it passed through the inner solar system. Oort was already well known in astronomy. He had spent years studying the structure and rotation of the Milky Way galaxy, mapping the motions of stars, helping to reveal that our galaxy was far larger than anyone had previously thought. He understood gravity, he understood orbits, and he understood that when numbers cluster in unexpected ways, they are trying to tell you something, and the numbers he was looking at were clustering. Oort calculated the aphelia for each of the 19 comets, the most distant points of their orbits, the places where they reached their farthest extent from the Sun before beginning the long fall back inward. What he found was striking. The aphelia were not scattered randomly across a broad range of distances, they clustered. Most of them fell within a specific range, roughly 20,000 to 50,000 AU from the Sun. The clustering was too tight to be coincidental. In statistics, when data points gather around a specific value without being forced to do so, it means something real is happening. Something physical. Something that demands an explanation. Oort reasoned carefully. If long-period comets were simply falling toward the Sun from random points in interstellar space, their aphelia should be distributed across an enormous range, scattered throughout the galaxy, but they were not. They clustered at a specific distance. That meant the comets were not interstellar wanderers. They were members of the solar system, orbiting the Sun at these enormous distances, occasionally getting nudged inward by some external force. The clustering pointed toward a structure. A reservoir. A vast shell of icy objects surrounding the entire solar system at distances thousands of times greater than Neptune's orbit. Oort was not the first person to suspect such a structure might exist. In 1932, nearly 2 decades earlier, an Estonian astronomer named Ernst Pick had proposed that a reservoir of comets might exist at the solar system's edge. Pick suggested that these distant objects could be perturbed by passing stars and sent falling toward the Sun. It was a brilliant intuition, but Pick did not have the data to prove it. His idea remained speculative. Interesting but unconfirmed. Oort had the data. He had the orbital statistics. He had the clustering. And he had something else. A physical mechanism that could explain how objects in stable distant orbits occasionally get knocked out of them and sent plunging sunward. That mechanism was stellar perturbation. Stars do not stay fixed in the sky. They move through the galaxy on their own orbits, each one circling the galactic centre at different speeds and different distances. The Sun is moving too, travelling through the Milky Way at roughly 450,000 miles per hour, completing one orbit around the galaxy every 230 million years or so. And occasionally over millions of years another star passes relatively close to the Sun. Not close enough to disrupt the planets. The planets orbit too tightly for that, but close enough to gravitationally nudge objects at the very outer edge of the Sun's influence. Objects whose orbits are so distant and so slow that even a faint gravitational tug from a passing star can change their trajectory. Those nudges can alter an icy body's orbit just enough to send it falling inward on a new path, one that eventually carries it past Jupiter, past Mars, past Earth, close enough to the Sun for its frozen surface to begin vaporizing into a glowing coma and tail. A comet is born, and its birth certificate reveals its home address, a region of space so far from the Sun that the boundary between the solar system and the galaxy itself begins to blur. Oort proposed that this reservoir was not a thin ring or a flat disk like the asteroid belt or the Kuiper belt. It was a sphere, a thick shell of icy objects surrounding the entire solar system at distances thousands of times greater than Neptune's orbit. The comets arriving from every direction in the sky made sense only if they were coming from a spherical source, not a flat one. He published his findings in 1950 in a paper that laid out the evidence carefully and systematically. The structure he described was eventually named the Oort Cloud in his honour, and in the decades since, every new line of evidence has strengthened the case for its existence. But Oort himself remained cautious about the numbers. In his original paper, he estimated the outer boundary of the cloud at somewhere around 50 to 100,000 AU from the Sun. Later models, incorporating better data and more sophisticated simulations, pushed some estimates even higher, to 150,000 or even 200,000 AU. Others suggested the cloud might be smaller or denser or shaped differently than a perfect sphere. The uncertainty reflects the fundamental challenge of studying something you cannot see. The Oort cloud has never been directly observed. Every claim about its size, mass and population is based on inference, cometary orbits, gravitational models, computer simulations. The cloud is known through its consequences, not its presence. But the consequences are undeniable. Long-period comets keep arriving, their orbits keep clustering, the mathematics keeps demanding a source, and no alternative explanation has ever come close to matching the simplicity and power of Oort's original insight. Convert the distances Oort proposed into more familiar units, and the result is staggering. 100,000 AU is approximately 1.5 light-years. 200,000 AU is over 3 light-years. The nearest star to the Sun, Proxima Centauri, sits at approximately 4.25 light-years away. This means the Oort cloud, if it extends to its estimated outer limits, may reach a quarter to more than halfway to the nearest star. The solar system does not end at Neptune. It does not end at the Kuiper belt. It does not end at the heliopause. It may extend so far into the darkness between stars that calling it a compact local neighbourhood becomes almost absurd. Oort gave humanity a new picture of home, not a diagram of 8 planets orbiting a star. A sphere of ice and darkness stretching across light years, with a tiny bright core at its centre where the warmth and light happen to be concentrated. The planets are not the solar system. They are the nucleus of something vastly, almost unimaginably larger. And yet, despite the elegance of Oort's work, despite the evidence accumulating year after year, the Oort cloud has never fully penetrated the public imagination the way the planets have. The planets are visible, dramatic, photogenic. The Oort cloud is invisible, silent and far. It does not make for good posters. It does not fit on diagrams. It resists visualization because the human brain simply cannot hold distances measured in light years and compare them honestly to distances measured in hours of sunlight. But it is there, surrounding us. Right now, trillions of frozen objects drifting in the dark, their orbits so slow that a single lap around the Sun takes longer than recorded human history. Some are the size of mountains, some are the size of cities. All of them are colder than anything you have ever touched, darker than any night you have ever experienced, and more isolated than any place on Earth. Jan Oort never saw the cloud that bears his name. He never photographed it. He never sent a spacecraft toward it. He simply looked at numbers, recognized a pattern, and deduced the existence of a structure so vast that it redefined the meaning of the solar system. That is the power of mathematics. That is the power of careful observation. 19 comets. 19 data points, and from them a vision of a frozen shell stretching light years into the dark, surrounding everything we have ever known. The cloud is named for him, but it belongs to all of us. It is the outermost edge of home. The Oort cloud is not a single thing. It is not a wall. It is not a uniform shell like the skin of an orange. It is layered, divided, shaped by different forces acting at different distances, sculpted over billions of years into a structure with distinct regions, each with its own character, its own density, its own relationship to the Sun and the galaxy beyond. To understand what the Oort Cloud actually is, you need to see it not as a simple sphere, but as an architecture. A vast construction with an inner zone and an outer zone, each built by different processes, each responding to different gravitational masters. The inner region is called the Hills Cloud, named after astronomer Jack Hills, who proposed its existence in 1981. It begins somewhere between 2000 and 5000 AU from the Sun, and extends outward to roughly 20,000 AU. Unlike the spherical outer cloud, the Hills Cloud is thought to be more flattened, shaped like a thick donut or torus, concentrated loosely around the plane where the planets orbit. This flattening is not random, it is a relic. The Hills Cloud contains objects that were scattered outward by the giant planets billions of years ago, flung into highly elliptical orbits before the galactic tide had time to fully randomize their paths. Because the scattering happened within the flat disk of the early solar system, the objects retained some memory of that original plane. Over time, the galactic tide has been working to erase that memory, rotating orbital planes and spreading objects into a more spherical distribution. But at the distances of the Hills Cloud, the process is slow. The flattening remains. The Hills Cloud is thought to be far denser than the outer cloud, containing perhaps 5 to 10 times as many objects. Some models suggest tens of billions, even hundreds of billions of icy bodies orbit within this inner zone. Yet even here, the distances between individual objects are enormous. You could travel for millions of miles through the Hills Cloud and never pass close enough to any single object to see it with the naked eye. Beyond the Hills Cloud, at roughly 20,000 AU, the outer Oort Cloud begins. This is the classical cloud, the one Jan Oort originally deduced from comet orbits. It extends outward to somewhere between 50,000 and 100,000 AU, with some estimates placing the absolute outer boundary as far as 150,000 to 200,000 AU from the Sun. The outer Oort Cloud is approximately spherical. Objects within it orbit the Sun at every inclination and in every direction. Some orbit in the same direction the planets do, others orbit backward. Some trace paths that are nearly circular at tremendous distances. Others follow highly elongated ellipses that carry them from the outer cloud deep into the inner solar system and back again over timescales measured in millions of years. The total population of the Oort Cloud remains uncertain because we cannot count objects we cannot see. But models based on the observed rate of long-period comet arrivals and the dynamics of how comets are dislodged from the cloud suggest staggering numbers. Conservative estimates place the population at several 100 billion objects larger than about half a mile across. More generous models propose 1 trillion or more. And yet, despite containing so many objects, the total mass of the entire Oort Cloud is believed to be modest, perhaps a fraction of an Earth mass to as much as several Earth masses, depending on the model. This may seem strange. How can a structure containing 1 trillion objects weigh so little? The answer lies in the objects themselves. The objects are small. Most are probably a few miles across or less, though some could be substantially larger. They are composed primarily of water ice, along with frozen carbon dioxide, methane, ammonia, and other volatile compounds mixed with dust and rock. They are primordial remnants, icy planetesimals left over from the formation of the solar system roughly 4.5 billion years ago, never incorporated into planets, never melted or altered by heat. They are dark. They reflect very little sunlight, which is itself vanishingly faint at their enormous distances. A typical Oort Cloud object receives so little solar energy that its surface temperature hovers just a few degrees above absolute zero, somewhere around 4 to 10 Kelvin. At these temperatures, even gases like nitrogen and carbon monoxide freeze solid. These are the coldest, most isolated objects in the solar system, drifting through near total darkness in orbits that take millions of years to complete. And they are sparse. The average density of the Oort cloud is so low that expressing it requires scientific notation pointing deep into the negative direction. If you calculated the average mass per cubic mile of Oort cloud volume, the resulting number would be so small it would take many decimal places just to reach the first digit that mattered. The Oort cloud is emptier than the best laboratory vacuums on Earth. It is emptier than the space between planets. It approaches the emptiness of intergalactic voids. This creates a paradox. The Oort cloud is simultaneously full and empty, full of objects, trillions of them, empty of matter in any experiential sense. If you flew a spacecraft through the Oort cloud, you would have no sensory evidence of its existence, no thickening of surrounding material, no increased frequency of impacts, no change in the star field outside your window. You could cross the entire cloud from inner edge to outer boundary, and never once encounter a detectable object, never once register a gravitational anomaly, never once have any reason to believe you are inside a structure at all. The Oort cloud is a ghost, written in gravity and statistics rather than in matter dense enough to see or touch. Why then do scientists believe this structure exists if it has never been directly observed? The answer comes back to the comets. Long-period comets have been arriving in the inner solar system for as long as humans have kept records. These comets follow orbits with periods exceeding 200 years, and many have periods measured in thousands or tens of thousands of years. When astronomers calculate the most distant points of their orbits, a consistent pattern emerges. Many long-period comets of aphelia clustered between roughly 20,000 and 50,000 AU. Others trace paths suggesting they originated from even greater distances. Critically, their orbital planes are randomly distributed. They arrive from every direction in the sky with no preferred orientation. This random distribution is the signature of a spherical source region. If long-period comets came from a flat disk, they would arrive preferentially from directions near the plane where the planets orbit. They do not. They come from above, below, and every angle in between. The only geometry consistent with this pattern is a shell, a vast sphere of source material surrounding the Sun at great distances. The evidence is not abstract. It arrives in our skies with names and dates and precisely measured trajectories. Every new long-period comet strengthens the case for the structure that sent it. Beyond the cometary evidence, there are objects like Sedna occupying the transition zone between the scattered disk and the inner Oort cloud, their orbits too detached from the planets to be explained by Neptune's gravity alone. These boundary objects represent the closest and most accessible fragments of a population that extends outward for tens of thousands of AU. The Oort cloud has architecture. It has layers. It has an inner region shaped by planetary scattering and an outer region shaped by the galactic tide. It has a population numbering in the hundreds of billions or trillions. It has a total mass that is surprisingly modest, spread across a volume so vast it defies comprehension. It is real. Not because we have photographed it, not because we have visited it, but because the mathematics of the comets we observe demands its existence. The orbits do not lie. The clustering is not coincidence. The spherical arrival pattern cannot be explained any other way. The Oort cloud surrounds us right now. A frozen shell stretching outward into darkness, containing more individual objects than every star visible to the naked eye, multiplied by millions. It is the outermost architecture of the solar system. the final layer. The edge that is not an edge, but a fading into something larger still. And understanding how this architecture came to exist, how trillions of icy objects ended up orbiting at such extreme distances, requires rewinding to the solar system's violent youth, when planets migrated and chaos ruled. 4.5 billion years ago, the solar system was not the orderly clockwork mechanism you know today. It was chaos. A swirling disk of gas and dust and countless rocky fragments, all orbiting a young star that had just ignited nuclear fusion in its core for the first time. Within this disk, solid particles were colliding and sticking together, gradually building larger and larger objects through a process that was part construction and part demolition derby. The biggest winners in this cosmic collision game became the planets. But the process was not gentle, it was not predictable, and it was certainly not finished once the planets had formed. What happened next shaped everything we see today, not just the planets themselves, but the asteroid belt, the Kuiper belt, and most importantly the vast frozen shell we now call the Oort Cloud. The story of how the cloud was born is a story of migration, violence and gravitational exile on a scale that defies easy comprehension. The formation model that best explains how all this material reached its current location is called the NICE model, named after the city in France where it was developed by a team of planetary scientists in the early 2000s. The NICE model describes a period of dramatic upheaval that occurred in the first several 100 million years after the planets formed, an era when the entire outer solar system reorganized itself, in an event so catastrophic that its effects are still visible today. In the NICE model, the giant planets originally orbited much closer to the Sun than they do now. Jupiter formed at roughly 5 AU, about where it sits today, but Saturn, Uranus and Neptune were packed much more tightly together, closer to the Sun and closer to each other. Beyond them stretched a massive disk of icy planetesimals, rocky and icy bodies that had formed in the outer solar system but never managed to gather into a planet. This disk contained perhaps 35 to 50 Earth masses of material. It was a vast reservoir of frozen mountains and icy boulders, each one orbiting the Sun in the same flat plane where the planets resided. For millions of years this arrangement remained stable. The giant planets orbited in their compact configuration. The planetesimal disk stretched outward beyond them, populated by countless objects ranging in size from boulders to small moons. It was a crowded, busy place, with frequent collisions and gravitational interactions, but the overall structure held together. Then, something shifted. Jupiter and Saturn, the two most massive planets, gradually migrated toward a specific orbital relationship called a mutual resonance, a configuration where their orbital periods became locked in a simple mathematical ratio. And when that resonance was crossed, everything changed. The gravitational balance that had kept the system stable for millions of years suddenly collapsed. Jupiter's immense gravity began to scatter objects more violently. Saturn's orbit began to change, and most dramatically, Uranus and Neptune were flung outward, migrating away from the Sun on trajectories that carried them directly into the massive disk of planetesimals beyond. What followed was a cosmic catastrophe. Uranus and Neptune, each weighing roughly 15 to 17 Earth masses, ploughed through the planetesimal disk like wrecking balls. Their gravitational influence scattered objects in every direction with tremendous force. Some planetesimals were flung inward toward the Sun, bombarding the inner planets in an episode that may correspond to what scientists call the Late Heavy Bombardment, a period roughly 4 billion years ago when the surfaces of Mercury, Venus, Earth and the Moon were pummeled by countless impacts. But the majority of planetesimals were scattered outward. Uranus and Neptune, as they migrated through the disk, acted like gravitational slingshots, flinging objects onto highly elongated orbits that carried them to enormous distances from the Sun. Most of these scattered objects were ejected entirely, launched on trajectories that carried them beyond the Sun's gravitational reach and into interstellar space forever. Computer simulations suggest that for every object that remained bound to the solar system, 10 or more were lost. But a significant fraction did remain bound. Their orbits were stretched to thousands, tens of thousands, even hundreds of thousands of AU, but they did not quite reach escape velocity. They became the Oort Cloud. However, the objects scattered by Uranus and Neptune were not immediately organized into the spherical shell we see today. Initially, their orbits were highly elongated and chaotic, carrying them far from the Sun, but bringing them back close enough to interact with the giant planets again and again. Many were eventually ejected on subsequent encounters. But those that survived faced a different fate. They were gradually reshaped by forces that had nothing to do with the planets at all. The most important of these forces was the galactic tide. The Sun sits within the Milky Way galaxy, surrounded by the combined gravitational influence of hundreds of billions of stars, vast clouds of gas and dust, and an enormous halo of dark matter. This collective gravitational field creates a tidal force that acts on everything orbiting the Sun. For the planets and for objects in the Kuiper belt, the galactic tide is negligible. The Sun's gravity overwhelms it completely. But for objects scattered to enormous distances, where the Sun's own gravity is weakened dramatically, the galactic tide becomes significant. Over millions of years, the galactic tide worked on these distant scattered objects, gradually modifying their orbits. It raised their perihelion distances, the closest points of their approaches to the Sun, pulling them away from the planetary region and preventing the giant planets from scattering them again. It also randomized their orbital inclinations, slowly converting the flattened disk-like distribution into a more spherical shell. This process, called galactic tidal evolution, effectively decoupled the scattered objects from the planets entirely, trapping them in stable orbits at great distances. They became gravitationally isolated, too far for the planets to reach, too close for the galaxy to strip away. They became the Oort Cloud. The process was not uniform. Objects scattered to different distances evolved at different rates. Those in the inner regions, between roughly 2,000 and 20,000 AU, were less affected by the galactic tide and retained more of their original flattened distribution. These became the Hills Cloud. Objects scattered to greater distances, beyond 20,000 AU, were more strongly affected by galactic tidal forces and became more thoroughly randomized into a spherical shell. These became the Outer Oort Cloud. The NICE model explains several puzzling features of the current solar system. It explains why the asteroid belt contains so little mass. Most of the original material was scattered away during the planetary migration. It explains the late heavy bombardment, objects flung inward during the chaos. It explains the current orbits of Uranus and Neptune, which show signs of having migrated outward from closer to the Sun. And most importantly for our story, it explains why the Oort Cloud contains material that originally formed between the giant planets but now orbits at distances measured in light years. The cloud is not made of interstellar material captured from space. It is made of solar system material that was violently expelled to the solar system's edge. The NICE model also explains why the Oort Cloud's total mass is relatively modest compared to the original planetesimal disk. Most of the disk's mass was lost entirely, either incorporated into the planets during their migration or ejected into interstellar space. Only a small percentage, estimated at 1 to a few percent, ended up trapped in the Oort Cloud. But even that small percentage, drawn from a disk containing tens of Earth masses, was enough to populate a cloud containing trillions of objects. The violence of this early period is difficult to overstate. The migration of Uranus and Neptune was not a gentle drift. It was a gravitational rampage that completely reorganized the outer solar system, scattering most of its contents into interstellar space and parking the survivors in a frozen shell at the very edge of the Sun's domain. The Oort Cloud is not a natural formation in the sense of being an inevitable outcome of planetary formation. It is a refugee camp, a vast collection of exiles scattered to the edge of the solar system by the gravitational equivalent of a natural disaster, then trapped there by the gentle but persistent pull of the galaxy itself. Every object in the Oort Cloud carries within its frozen structure the chemical signature of the early solar system, preserved in ice that has not melted since the chaos ended 4 billion years ago. The cloud was born in violence. It has lived in silence ever since, and the forces that shaped it, planetary migration, galactic tides, stellar encounters, continue to sculpt it. Today, the Oort Cloud is not a museum. It is not a static collection of frozen relics gathering dust in the outer darkness. It is alive, not in any biological sense, but in a gravitational sense, responding continuously to forces that reach across the galaxy itself. Every object in the cloud is being gently pulled, nudged, and gradually reshaped by influences that originate far beyond the solar system, forces so subtle that they operate over millions of years, but so persistent that they have been sculpting the cloud's architecture since it formed. The Sun is not alone in the galaxy. It is one of roughly 400 billion stars orbiting the centre of the Milky Way, each following its own path through the galactic disk at different speeds and different distances from the centre. The Sun travels at approximately 450,000 miles per hour relative to the local galactic environment, completing one orbit around the galaxy every 230 million years. As it moves, it encounters regions of varying stellar density, sometimes passing through the sparse spaces between spiral arms, sometimes crossing through the denser stellar neighbourhoods within them. And occasionally, not often, but regularly over millions of years, another star passes close enough to the Sun for its gravity to reach into the Oort Cloud and stir things up. The most dramatic upcoming encounter that astronomers have identified involves a small orange dwarf star called Gliese 7 Currently about 64 light-years away, Gliese 7 is heading almost directly toward our solar system. Based on precise measurements from the European Space Agency's Gaia spacecraft, astronomers have calculated that in approximately 1.3 million years, Gliese 7 will pass through the inner Oort Cloud at a distance of roughly 10 to 13,000 AU from the Sun. This may sound distant, but in Oort Cloud terms, it is catastrophically close. A star passing within 13,000 AU will have enough gravitational influence to disrupt the orbits of millions or billions of Oort Cloud objects. Some will be flung outward, their orbits stretched until they escape the solar system entirely, lost to interstellar space forever. Others will have their orbits deflected inward, their perihelion distances lowered enough that they begin falling toward the inner solar system for the first time in billions of years. Over the million years following Gliese 7's passage, Earth's skies will experience a comet shower unlike anything in recorded human history. New long-period comets will arrive regularly, visitors dislodged from the Oort Cloud's outer reaches by the gravitational handshake of a passing star. Some will be spectacular. Some will be barely visible. All of them will carry ice that has been frozen since the solar system was young, suddenly heated and vaporized by sunlight for the first time since they were scattered to the edge of the Sun's domain. This is not an unusual event. It is routine. Over the 4.5 billion years of the solar system's existence, hundreds or thousands of stars have passed through or near the Oort Cloud. Each passage has stirred the population, ejecting some members, redirecting others, feeding the continuous supply of comets that arrive in the inner solar system. The Oort Cloud has been shaped by these encounters, carved and sculpted by stellar visitors that come and go on timescales measured in millions of years. But stellar encounters are not the only force at work. There is another influence, more subtle but more persistent: the galactic tide. The Milky Way galaxy is not uniform. Its mass is distributed in complex patterns: a dense central bulge, spiral arms containing young stars and gas clouds, a vast halo of dark matter extending far beyond the visible disk. The Sun sits within this structure, about 26,000 light-years from the galactic centre, orbiting through regions where the gravitational environment changes subtly over time. This changing gravitational environment creates a tidal force that acts on everything orbiting the Sun. The force is extraordinarily weak compared to the Sun's gravity, so weak that it has no measurable effect on anything in the planetary region. But at the enormous distances of the Oort Cloud, where the Sun's own gravity has weakened dramatically, the galactic tide becomes significant. The galactic tide acts on Oort Cloud objects by slowly rotating their orbital planes and modifying their eccentricities over millions of years. It can raise perihelion distances, pulling objects away from the planetary region and effectively parking them in stable orbits at great distances. It can also lower perihelion distances, sending objects that have been orbiting safely in the outer clouds spiraling inward toward the Sun. When the galactic tide lowers an Oort Cloud object's perihelion enough that it begins to interact with the giant planets, the object enters the inner solar system as a new long-period comet. This process has been operating continuously for billions of years. It is why new comets keep arriving, even though each comet that passes close to the Sun eventually evaporates and is lost. Research over the past several decades has revealed that the galactic tide and stellar perturbations do not operate independently. They work together in a complex synergy first described by astronomers Hans Rieckmann, Marc Fouchard, and their colleagues. The galactic tide provides a steady background evolution of Oort Cloud orbits over long timescales, while passing stars inject bursts of random perturbation that can dramatically accelerate the process. This synergy explains why the supply of long-period comets remains relatively steady over time, rather than arriving in dramatic pulses. The two mechanisms complement each other, maintaining a continuous trickle of comets from the outer reservoir into the inner solar system. There is a third mechanism that adds another layer of complexity. Computer simulations by astronomers Nathan Kaib and Thomas Quinn have shown that comets from the inner Oort Cloud, the Hills Cloud region, can also reach the inner solar system, but through a different pathway. Objects in the Hills Cloud are too tightly bound to the Sun for the galactic tide or passing stars to directly inject them into planet-crossing orbits. However, gravitational interactions with the giant planets can scatter some of these objects outward into the outer Oort Cloud, where external forces then redirect them inward. This creates a flow of material from the Hills Cloud to the outer cloud and then to the comet population, making the Oort Cloud a dynamically evolving system rather than a static reservoir. Objects can spend millions of years in the Hills Cloud before being kicked to the outer cloud, then millions more years in the outer cloud before being sent toward the Sun. Some arrive disguised as apparently pristine comets from the outer cloud, even though they originally resided much closer. The Oort Cloud breathes. It inhales material scattered outward from the inner solar system and exhales comets toward the Sun. It loses members to stellar perturbations and gains members from planetary scattering. Its population churns over billions of years, continuously reshaped by forces that operate on galactic timescales. Understanding these processes reveals something profound about the nature of the Oort Cloud. It is not simply the solar system's outer boundary. It is the region where the solar system and the galaxy intersect, where the Sun's gravitational domain meets and mingles with the gravitational influence of 400 billion other stars. The forces that shape the Oort Cloud are the same forces that shape the galaxy itself. The cloud is not separate from the Milky Way, it is part of the Milky Way's structure, a local concentration of matter held in place by one star's gravity but continuously modified by the collective influence of all the others. This means every comet that blazes across Earth's sky carries information not just about the early solar system, but about the galactic environment the Sun has travelled through over billions of years. Each comet is a messenger from both the solar system's past and the galaxy's influence, a frozen sample of ice that has been stirred and shaped by forces operating across light years of space and eons of time. The Oort Cloud is where the solar system touches the galaxy, and the galaxy, it turns out, has been sculpting the cloud in ways that no one expected. Sometimes the most profound discoveries happen by accident, in places where no one was looking for them. This is the story of how a spiral galaxy pattern was found hiding in the outer reaches of our own solar system, written into the architecture of the Oort Cloud itself. A discovery made not through a telescope, not through years of careful observation, but inside a planetarium dome in New York City. In September 2024, curators at the Hayden Planetarium in Manhattan were preparing a new show called Encounters in the Milky Way. The show was designed to take visitors on a journey through galactic space, illustrating how our solar system moves through the galaxy and encounters other stars over millions of years. To make the presentation as accurate as possible, they had contacted David Nesvorn, a planetary scientist at the Southwest Research Institute, who had spent years modelling the Oort Cloud's formation and dynamics using some of the world's most powerful supercomputers. Nesvorn provided them with detailed simulation data, the positions and orbits of hundreds of thousands of Oort Cloud objects as calculated by his models. The planetarium team began building their visualization, projecting the three-dimensional data onto the curved dome to create an immersive experience for visitors. When astrophysicist Jackie Farity saw the first test projection, something in the visualization made her stop. There, clearly visible in the inner Oort Cloud region, were two distinct spiral arms curling outward like a miniature galaxy. The pattern was unmistakable, a two-armed spiral structure approximately 15,000 AU across, oriented roughly perpendicular to the galactic plane. At first, Nesvorn suspected the spiral was an artifact. Perhaps the visualization software had introduced a distortion. Perhaps the way the data was being rendered onto the dome was creating a pattern that wasn't really there. Computer simulations are complex, and sometimes the process of converting mathematical calculations into visual displays can produce misleading results. But when Nesvorn went back to examine his raw simulation data, the actual numerical output from his supercomputer models, the spiral was there too. He had simply never looked at the data in the three-dimensional Cartesian coordinates that the planetarium projection used. In his standard analytical framework, focused on orbital elements and statistical distributions, the structure had been invisible. Viewed from the right perspective, it was clear and undeniable. Nesvorn used NASA's Pleiades supercomputer to run additional simulations, testing whether the spiral persisted under different parameters, different stellar encounter histories, and different initial conditions. Every simulation produced the same basic structure, a stable two-armed spiral in the inner Oort Cloud, clearly defined and remarkably persistent over billions of years. The discovery was both surprising and elegant. For decades, the standard picture of the inner Oort Cloud, the Hills Cloud region between roughly 1,000 and 20,000 AU, had been relatively featureless. Scientists understood it to be more flattened than the outer cloud, shaped more like a thick donut than a perfect sphere. But they had not expected it to possess internal architecture as organized as a spiral pattern. The physical explanation, once Nesvorn worked it out, was beautiful in its simplicity. Objects in the inner Oort cloud exist in a unique gravitational environment, close enough to the Sun that solar gravity still dominates, but far enough away that the galactic tide becomes a significant secondary influence. The galactic tide is the gravitational pull exerted by the combined mass of all the stars, gas and dark matter in the Milky Way galaxy, and it acts on Oort cloud objects by slowly modifying their orbits over millions of years. The key insight was that this galactic tidal influence does not act uniformly on all objects. Its effects depend on each object's specific orbital parameters, its distance from the Sun, its inclination, its eccentricity. Objects at different distances and with different orbital characteristics evolve at different rates under the galactic tide's influence. This differential evolution, governed by a phenomenon known as Kozai-Lidov oscillations, creates a systematic twisting pattern over billions of years. The result is that objects in the inner Oort cloud do not simply orbit randomly. They organize themselves into streams and concentrations that, when viewed in the right coordinate system, form a clear spiral structure. The pattern emerges naturally from the interaction between solar gravity and galactic tides, the local influence of our star competing with the distant but persistent pull of the galaxy itself. The spiral is remarkably stable. Nesvorn's simulations showed that it formed early in the solar system's history, within the first few 100 million years after the Oort cloud was populated, and has persisted essentially unchanged to the present day. Even close stellar passages, which can temporarily disrupt parts of the outer Oort cloud, leave the inner spiral largely intact, because the objects composing it are more tightly bound to the Sun and less susceptible to external perturbation. The discovery was published in February 2025 in a paper that appeared first on the RxIV preprint server and was later accepted for publication in the Astrophysical Journal. It represents what scientists call a prediction, a finding from theoretical models that has not yet been independently confirmed through direct observation. And direct observation remains a formidable challenge. To map the spiral structure observationally would require identifying and tracking hundreds or thousands of individual Oort cloud objects, a task that pushes the limits of current technology. The objects are small, dark, and separated by enormous distances. They reflect almost no light and are too faint for existing telescopes to detect reliably. The Vera Rubin Observatory, which began operations in Chile in 2024, represents the best hope for detecting Oort cloud objects in significant numbers. Its legacy survey of space and time is designed to map the entire visible sky repeatedly over 10 years, and it may discover dozens of individual Oort cloud members through their slow motion against the background stars. But dozens are not enough to map a spiral pattern. Hundreds would be needed to produce a meaningful visualization of the structure. Nesvorn himself has noted that confirming the spiral observationally may require technological advances beyond what currently exists. The pattern is real in the models, supported by solid physics, but proving its existence in the actual Oort cloud will likely take decades. Still, the discovery is significant for what it reveals about the Oort cloud's true nature. For decades, astronomers had thought of the cloud as a relatively simple structure, an inner region that was somewhat flattened and an outer region that was roughly spherical. The spiral finding suggests that the Oort cloud possesses sophisticated internal architecture, shaped not just by the Sun and the planets, but by the galaxy itself. The Milky Way's gravitational field has literally sculpted the structure of the solar system's outermost region, twisting it into a pattern that resembles, on a vastly smaller scale, the spiral arms of the galaxy that created the force responsible. The inner Oort cloud carries the fingerprint of the Milky Way written into its shape. This discovery reinforces a deeper point about the Oort Cloud's nature. It is not a static fossil from the solar system's formation. It is a dynamic structure, continuously shaped by forces operating on timescales of millions and billions of years. The galactic tide rotates orbits, passing stars dislodge members. Planetary scattering feeds new material outward. The cloud itself responds to these influences like a living system, reorganizing its internal structure in response to the gravitational environment around it. The spiral was always there, hidden in the data, waiting for someone to look at it from the right angle. It took a planetarium dome and an astrophysicist's trained eye to reveal that the solar system's outermost structure contains architecture as elegant and organized as anything in the galaxy beyond. The Oort Cloud has secrets written into its shape. The spiral is probably just the first one we have learned to see. There is a difference between knowing a number and feeling it. You can read that the Oort Cloud extends to 100,000 AU from the Sun and understand the sentence perfectly. The words are clear, the number is specific. But the sentence does not land. It slides past your mind the way statistics about national debt slide past, technically comprehended, but emotionally weightless. The number is too large for your brain to convert into anything resembling experience. This is not a failure of intelligence, it is a feature of human cognition. Your brain evolved to track distances you could walk, territories you could cross in a day or a season. Your ancestors never needed to process numbers requiring scientific notation. When distances exceed a few hundred miles, your mental mapping software begins to approximate. When they reach billions or trillions of miles, it simply gives up, replacing genuine spatial comprehension with a vague emotional label, very far. The Oort Cloud operates at distances where that label becomes dangerously inadequate. To understand what the Oort Cloud means for the solar system, you need to feel the scale, not just hear it. And the only way to feel it is to build it up layer by layer, comparison by comparison, until the structure assembles itself in your mind, and your old picture of the solar system breaks apart under the weight of what it was always missing. Start with something you can hold. The distance from Earth to the Sun is 1 astronomical unit, roughly 93 million miles. Light covers this distance in about 8 minutes and 20 seconds. If you could drive at highway speed without stopping, the trip would take roughly 177 years. That is the baseline. 1 AU, the measuring stick for everything that follows. Neptune, the outermost planet, orbits at 30 AU. Light from the Sun reaches Neptune in about 4 hours. At highway speed, driving to Neptune would take roughly 5,300 years. You would have set off before the construction of Stonehenge and still be driving today. This is the outer boundary of the planetary solar system, the edge of the familiar diagram. Now step into the Oort Cloud. The inner edge of the Hills Cloud begins at approximately 2,000 to 5,000 AU from the Sun. Take the conservative estimate, 2,000 AU. That is already 67 times farther from the Sun than Neptune. Light from the Sun takes about 11 days to reach this point. At highway speed, the drive would take 354,000 years. But 2,000 AU is only the threshold. It is where the Oort Cloud begins, not where it ends. The Hills Cloud extends outward to perhaps 20,000 AU. At that distance, sunlight needs about 4 months to arrive. You are now 667 times farther from the Sun than Neptune. The Sun still dominates gravitationally, but just barely. From the outer reaches of the Hills Cloud, the Sun appears as an exceptionally bright star, visually indistinguishable from other bright stars, except for the fact that your orbit still traces a vast, lazy ellipse around it. Continue outward. The outer Oort Cloud begins beyond the Hills Cloud and extends to at least 50,000 AU. At this distance, the sun's light takes approximately 9.5 months to arrive. You are now roughly 4/5 of a light year from the sun. The sun still shines as the brightest star in your sky, roughly as luminous as Jupiter appears from Earth. But it is nothing more than a point, no disk, no perceptible warmth across that staggering vacuum. Pushed to the estimated outer boundary, 100,000 AU. This is the distance most commonly cited as the Oort Cloud's outer limit. At 100,000 AU, you are approximately 1.5 light years from the sun. Sunlight needs a full 1.5 years to reach you. The sun still shines as one of the brightest stars visible, easily found if you knew where to look. But that bright point delivers no more heat than any other star, which is to say, effectively nothing. And you are still inside the solar system. 1.5 light years. Proxima Centauri, the nearest star to the sun, lies at approximately 4.25 light years. If the Oort Cloud's outer edge sits at 1.5 light years, then the sun's domain extends more than 1/3 of the way to the nearest neighbouring star. Some estimates push the boundary to 2 or even 3 light years, meaning the solar system might reach halfway to Proxima Centauri. To make this scale concrete, consider time. Voyager 1, currently the most distant human-made object, has been travelling outward from the sun at roughly 38,000 miles per hour for nearly 50 years. As of 2026, it sits approximately 165 AU from the sun, not yet 1/5 of 1% of the way to the Oort Cloud's outer edge. At its current speed, Voyager 1 will reach the inner edge of the Oort Cloud in roughly 300 years. It will not exit the outer boundary for approximately 30,000 years. 30,000 years. When Voyager 1 finally leaves the Oort Cloud, the entire span of recorded human history will have elapsed roughly once during the crossing. The spacecraft will have been travelling continuously for longer than humans have had writing, agriculture, or permanent settlements. Radio signals, travelling at the speed of light, fare only somewhat better. If humanity ever sent a probe to the Oort Cloud's outer edge, a command transmitted from Earth would take 1.5 years to arrive. The probe's reply would take another 1.5 years to return. 3 years of silence between a question and its answer. If something went wrong, mission controllers would not learn about the failure until 18 months after it happened. The scale becomes even more visceral through volume. Volume scales with the cube of radius. If the Oort Cloud's outer boundary is more than 3,000 times farther from the Sun than Neptune, then the volume of the Oort Cloud sphere is roughly 37 billion times larger than the volume of the sphere enclosing the planetary solar system. All 8 planets, all their moons, all the asteroids and Kuiper Belt objects exist within a volume that represents less than 1/billionth of the Sun's gravitational domain. Think of it this way. If the Oort Cloud were a sphere the size of Earth, the planetary solar system at its centre would be a sphere roughly 4 kilometres across. A small hill town swallowed inside an entire world. Or consider the classroom scale model that teachers have built with students for decades. You place a basketball at one end of a schoolyard to represent the sun, then walk outward placing smaller objects at scaled distances. A peppercorn for Mercury, a marble for Earth, a ping-pong ball for Jupiter. By the time you reach Neptune, represented by a small bead, you have walked perhaps half a mile, but in a model where Neptune sits half a mile from the basketball sun, the inner edge of the Oort Cloud would begin roughly 33 miles away. The outer edge would sit approximately 1,600 miles away. The model that fit comfortably in a schoolyard for the planets would need to stretch from New York City to Denver to include the Oort Cloud. The basketball sun sits on a sidewalk in Manhattan, and the outer boundary of the solar system is in Colorado. Every schoolyard model ever built has been teaching students a truncated lesson, showing them the lit core and cutting off the structure before it reveals its true size. This ratio carries mathematical consequences that are easy to state and difficult to absorb. The familiar solar system, Mercury through Neptune, occupies roughly 1/10% of the Sun's total gravitational reach. Every mission NASA has ever flown, every planet humanity has photographed, every probe that has returned data from the outer solar system has operated within the innermost fraction of 1% of the Sun's domain. The planetary solar system is not a summary of home, it is the front porch light on a house that stretches for light years into the dark. Everything you have ever heard described as the edge of the solar system, Neptune, Pluto, the heliopause, Voyagers crossing into interstellar space, exists within the first fraction of 1% of the structure's actual extent. Now reconsider the classroom diagram that has shaped every mental model of the solar system since childhood. That neat row of planets stretching from Mercury to Neptune represents a region of space so tiny relative to the Oort Cloud that no honest diagram could show both on the same page. If you drew the Oort Cloud as a circle filling a classroom wall, the planetary solar system would be smaller than the period at the end of this sentence. The diagram did not lie through malice. It lied through the impossibility of representing these scales honestly. But the lie has consequences. It gave billions of people a mental model of home that is missing 99.9% of home. The Oort Cloud is not an addition to the solar system. By volume, the solar system is the Oort Cloud. Everything else is a bright, warm, busy speck at its centre, important to us because we live there, but cosmically insignificant compared to the vast dark sphere that constitutes nearly all of the Sun's gravitational territory. The scale is not merely large, it redefines what the solar system is. Every map humanity has ever drawn required an edge, the coastline of a continent, the border of a nation, the property line of a backyard. Maps work because they have boundaries, clean lines separating what belongs inside from what belongs outside. The human mind craves these boundaries. It organizes reality by sorting things into containers with defined limits. This is home. That is elsewhere. Beyond this line, something different begins. The solar system was supposed to have an edge. For centuries, that edge was implicit in every diagram, every model, every description of our cosmic neighborhood. The planets orbit the Sun. Beyond the last planet, the solar system ends. Interstellar space begins. A clean line, a clear boundary. Inside is home, outside is the void. The Oort Cloud destroys this boundary. It does not blur it slightly. It does not push it outward to a new farther location where a clean line can be redrawn. It eliminates the concept of a boundary entirely. The Oort Cloud reveals that the solar system does not end. It fades. And the region across which it fades is so vast, so gradual, and so interpenetrated with the forces of the wider galaxy that no line can be drawn anywhere without being arbitrary. At the centre of the solar system, the Sun's gravity is overwhelming. Mercury orbits in 88 days. Moving outward, that grip weakens. Neptune takes 165 years to complete a single orbit. In the Oort Cloud, the leash becomes gossamer. At 50,000 AU, an icy body orbits the Sun once every 10 million years or more. Its orbital velocity is measured in fractions of a mile per hour. It drifts. But here, at these enormous distances, other forces begin to compete with the Sun's gravity on nearly equal terms. The most important is the galactic tide, the combined gravitational influence of 400 billion stars, vast clouds of gas and dust, and an enormous halo of dark matter distributed throughout the Milky Way. For objects close to the Sun, the galactic tide is negligible. But as you move outward through the Oort Cloud, the Sun's gravity weakens, while the galactic tide remains constant. At some critical distance, the two forces become comparable. Beyond that distance, the galaxy's gravitational influence exceeds the Sun's. Objects can no longer maintain stable orbits. They are stripped away, claimed by the Milky Way, lost to interstellar space. This transition distance roughly corresponds to the Oort Cloud's outer boundary, not because there is a wall there, but because that is as far as the Sun's gravitational authority extends. But this transition is not a clean break. It is a gradient. There is no distance at which the Sun's gravity suddenly drops to zero, and the galactic tide suddenly activates. Both forces operate continuously. What changes is their ratio. At the outer edge of the Oort Cloud, the Sun's hold on individual objects becomes tenuous, contingent, uncertain. Some objects at these distances are bound to the Sun, others are not. The difference depends on orbital specifics and the particular gravitational disturbances each object has experienced over billions of years. This means the solar system's outer edge is not a boundary in any physical sense. It is a probability distribution. The fraction of objects gravitationally bound to the Sun decreases gradually with distance, until essentially none remain. There is no point where you cross from inside to outside. There is only a vast transitional region where belonging to the solar system becomes progressively less meaningful. And the transition is not sealed. Material crosses it in both directions continuously. We have proof. In October 2017, astronomers detected an object moving through the inner solar system on a trajectory that was unmistakably interstellar. Its orbit was hyperbolic, meaning it was not bound to the Sun. It had entered from outside, swung past the Sun, and was departing, never to return. The object was named Oumuamua, a Hawaiian word meaning scout from afar. 2 years later, amateur astronomer Gennady Borisov discovered a second interstellar visitor, Comet 2I Borisov. Unlike Oumuamua, Borisov was clearly a comet, displaying a bright coma and tail as it approached the Sun. It was a piece of another star's Oort Cloud, ejected from its home system and wandering the galaxy until chance brought it through ours. These detections revealed that the solar system is not sealed. It is permeable. Objects from other stellar systems drift through our territory, while objects ejected from our Oort Cloud drift through theirs. The interstellar medium is populated by a diffuse rain of icy and rocky bodies ejected from countless Oort clouds around countless stars, forming a background population that passes through every stellar system in the galaxy. If this is true, then other stars likely possess their own Oort clouds. Proxima Centauri, at 4¼ light-years away, probably sits at the centre of its own vast shell of frozen debris. If that cloud extends outward for 1 to 2 light-years, as models suggest it might, then the gap between our cloud and theirs is only about 1 to 2 light-years wide. In this picture, the space between stars is not empty desert with isolated oases scattered through it. Each star sits at the centre of an enormous gravitational domain, its territory extending outward until it begins to overlap with the territories of its neighbours. The galaxy becomes a mosaic of overlapping spheres of influence, each defined by an outer shell of icy debris slowly orbiting a distant point of light. The boundary between stellar systems was breached at the very beginning and has never been sealed since. Our Oort cloud already contains material captured from other stars during the Sun's youth, when it was embedded in a dense cluster of siblings. The cloud we inhabit today is not purely ours. It is a mixture of local debris and imported material, blended together over billions of years. This realization transforms the meaning of home. Home extends for light years in every direction. Home is mostly dark. Home includes trillions of frozen objects drifting in near total isolation. Home reaches so far into the darkness between stars that it begins to blend with the territories of neighbouring suns. And home is not permanent. It breathes, expanding and contracting as the sun travels through different galactic environments over hundreds of millions of years. You are not standing on a small world orbiting a star in empty space. You are standing on a warm island at the centre of a vast gravitational ocean that stretches outward into regions where the sun is just another bright point in a crowded sky. The ocean has currents. It has tides. It exchanges material with other oceans around other stars. And somewhere in its farthest reaches, objects the size of mountains drift in absolute silence, through darkness so complete that the sun's light, when it finally arrives, provides no more warmth than starlight. Yet even there, in that remote and frozen realm, those objects are still orbiting. Still held, still home. The thread of gravity that connects them to the sun, and therefore to Earth, and therefore to you, stretches across distances measured in light years, but has never broken. Not in 4.5 billion years. That thread connects you to trillions of ancient ice worlds you will never see, drifting in orbits so slow that a single revolution takes longer than human civilization has existed. They are your most distant neighbours. Silent cousins. Frozen memories of the solar system's birth, preserved in darkness at the very edge of what the sun can claim as its own. As you rest tonight, Earth turning gently beneath the stars, that vast shell of ice continues its ancient dance around the sun. Invisible. Patient. Eternal. The true edge of home fading gradually into the galaxy itself, with no clear line between where you belong and where the universe begins. In the end, there is no boundary. There is only the quiet expansion of belonging, stretching outward from your warm bed into the dark, until the solar system becomes the galaxy, and the galaxy becomes the cosmos, and you discover that home was always larger than you dreamed. Rest now. The Oort Cloud keeps watch,